Okay, good morning. In this video, we are going to see a subtopic, namely the existence and uniqueness of minimal polynomial under the theory of single linear transformation. Um, okay, so before we get into that, let us recall some of the tools that we already know, and some of the assumptions that we need. So let's assume that let us assume that let V be V be an n-dimensional vector space over an arbitrary field f. Okay, arbitrary field f. Okay. So once we know that V is an n-dimensional vector space over f, then immediately we know that L of V comma V is also a vector space over f. So this vector space gives two structures for us, namely the addition from L of V comma V. I mean, we know how to add two linear maps, and we also know how to multiply a scalar with this linear map. These are the structures given by this vector space concept. So this is known. Similarly, we also know that once we fix a basis of V, let's say let V1, V2, etc. up to Vn be any basis of V, then we know that then for any linear map f belonging to L of V comma V, for any linear map f belonging to L of V comma V, we know that there exists a matrix representation of this linear map in coming from Mn of f. Okay. In fact, we know that once we fix a basis of LV1, V2, Vn as a basis of V, then we know that L of V comma V can be proved to be isomorphic to this n square tuple over the field f. I mean, this Mn of f can be seen as a n square tuple. I use a notation of small f. Okay, somehow I don't know, from my early age I use the small f. Normally books uses the capital T and all that, so you can use that, but I use the small f notation, which I am comfortable with. Okay. I mean, what I mean to say is, in general, linear transformations are represented by capital T or U or V, but I am somehow comfortable with the F, so I am using it. So don't get confused with that. And we also know that from algebra, we also know that L of V comma V is a non-commutative ring with identity. That means we know the same addition which we have seen before, and we also have a structure of multiplying two linear maps, which is nothing but the composition of functions, and therefore we have the structure of function this one. These are the structures which we already know, being a ring or a vector space and all that. We also have to recall, and we also have to see a new structure now. This structure is between polynomial ring over the field f and L of V comma V. Okay, so we try to show that there exists a function called multiplication, where you can multiply a polynomial ring and multiply a polynomial from the polynomial ring and the linear maps and the linear map. Okay. So we know that this guy is a commutative ring with identity element, and this is a non-commutative ring. Therefore, this structure will also gives us to identify elements which commutes here. Okay. So we will see that. Anyway, I mean, this is anyway we are already comfortable with by multiplying we are already comfortable with multiplying a scalar and a vector. So this is something similar to that. The only thing is, this scalar is not a field. That is the only difference. Not a field. That's the only difference. I mean, there is a generalization of vector space concept called module theory. People who are interested in this, they can refer to this module theory, where the scalars are not necessarily going to come from the field. I mean, the scalars are going to come from more abstract space of rings. Okay, so this thing. I mean, this we have seen already. This structure we have seen already, but we have not put it as this forward. So for beginners, this may be initially a few. Initially you may not be comfortable with it, but try to see this. It's not a not a very irrational one. this is already known to us, but we are just seeing a new structure form. So, what we mean is, in other words, so if you have a polynomial, say a of x belonging to f of x, take a polynomial and you take an arbitrary linear map, f belongs to L of v comma v, say a of x can be, notation wise a of f can be written as summation k running from 0 to L alpha k x to the power k, where alpha k belongs to the field f. It is a polynomial, and so we are going to bring this structure. So, this structure is given as a of x with f is mapped to a of f. So, what we do is we just replace x by f and see and say that the resulting one, I mean we have to show that the resulting one is a linear map. So, it is simple. So, what we get is summation k running from 0 to L alpha k f power k. So, what is this? This is nothing but this is nothing but alpha naught into I plus alpha 1 f plus etcetera up to alpha L f to the power L. Okay. So, very easy to see that given f, since f is in L of v comma v, I mean using ring structure we can easily say that f power k is in L of v comma v. So, what is f power k is the composition of functions. So, f power k is defined as f composition k times therefore, f power k belongs to L of v comma v, and since L of v comma v is a vector space, any alpha k times of alpha k times of f k is also a linear map for any alpha k in the field over which L of v comma v is a vector space, and therefore and again you can also sum over this for various, okay, let us say L here, and we can also sum over for L from 0 to k. Again you have addition, since L of v comma v is a vector space, and therefore hence we have proved that this way of multiplying, this way of multiplying a polynomial and set of and linear maps is a function. Therefore, this algebraic structure can be used, okay, in our further things. One interesting thing that we have to observe here is this L of v comma v, which is the set we are studying now, has a multiple phase. Okay, has a multiple phase. I mean L of v comma v, in one side you can see it as a vector space, okay, with addition and multiplication. So, I will call it as L for simple notation, addition and scalar multiplication from this to this. Another side you see it as a non commutative ring with identity element, with the same addition and multiplication of functions, composition of function. And the third phase of it is you also have a structure of multiplying a polynomial and linear map. Okay. So, these guys have a multiple phase, and we have to handle and we have to use it when we want to understand the structure of a single linear transformation coming out of the set. So, that is the thing. One advantage of this structure is we know that this is a commutative ring and this is a non-commutative ring. Therefore, for example if we take two polynomials, say a of x and b of x, we know that a of x b of x is equal to b of x into a of x, where a and b, we are taking a of x, b of x both belonging to the polynomial ring. Okay. Therefore, since we know that it is a commutative ring with the end element, this is well known. Now, if you replace, let us say take a linear map f, and then if you replace x by f by using this structure, then you know that this is also true. Otherwise this negates that this guy is a function. Therefore, this has to be equal, and therefore this says that these two linear maps are also commuting. Therefore, indirectly this kind of this structure helps us to find linear maps in L of v comma v which commutes. Okay. So, this is a very useful structure and helps us to helps us in various forms. Okay. So, we will see that. Okay. So, let us get into the thing that we want to say. So, we wanted to prove that. So, let f be any arbitrary linear map in L of v comma v, So we know that since we know that L of v comma v, we know the dimension of L of v comma v is n square, and therefore this tells you that if I take I f square etc. up to f to the power n square, then this set is linearly dependent because this is n square plus 1 elements in L of v comma v, and L of v comma v is n square dimension. Therefore, any n square plus 1 set is linearly dependent. Therefore, this is clear. Now we claim that there exists an integer k, okay, there exists an integer k less than or equal to n square, such that I f square etc. up to f to the power k minus 1 is linearly independent, and I f etc. up to f to the power k is linearly independent. Okay. So, we claim this. Now, the proof can be given constructively. So, I mean, we know that singleton I is a non-zero element of L of v comma v is linearly independent. Okay. So, that is fine. Now, if we take the set I and f, there are two choices, either this set is linearly independent or the set is linearly dependent. Suppose if it is linearly dependent, then we have shown the claim that the k is 1, and we have shown that k is 1 and I is linearly independent and I and f are linearly dependent. So, suppose if it is linearly dependent, then we have shown the claim. Suppose if it is linearly independent, then consider the set I f square. Again, you have two choices. This set may be linearly independent or this set may be independent. If it is linearly dependent, then you have shown that k is 2 and I and f is linearly independent and I and f square is independent. Now, suppose it is not linearly dependent. If it is linearly independent, suppose, then you consider I f square and f cube. Again, you can do the same logic. Now, the good thing is, there is an upper bound for this thing, because we know that at some stage we know that the whole set is linearly dependent. The set is linearly dependent. Therefore, naturally this set is bounded above by k. Therefore, there is a k which is bounded above by n square. At some stage it is going to be linearly dependent. Okay. Therefore, this claim is very clear by this argument that there exists a k. This implies there exists a k, an integer less than or equal to n square, such that non-negative integer less than or equal to n square, such that I f square etc. up to f power k is f power k minus 1 is linearly independent, and I f square etc. up to f to the power k is linearly dependent. Of course, set notation, just put it in the set, they are set. The set vectors is independent. Therefore, that is what we wanted to prove, and we have proved this. Okay. Therefore, this implies, now this implies that I f square etc. to f power k is linearly dependent implies that since it is a linearly dependent set, we know that at least one of the vector will be written as a linear combination of other. So, without losing generality, we can assume that f k is written as a linear combination of the other, because the set is linearly independent. Now, we say that this implies that there exist let us say alpha naught, alpha 1 etc. up to alpha k minus 1, such that f k is nothing but summation L running from 0 to k minus 1 alpha L f to the power L. So, I assume that f power 0 is I. Okay. That is what I assume. I will use the next page. Okay. So, what we have shown now is, that f k is nothing but summation L running from 0 to k minus 1 alpha L f to the power L. Therefore, this can also be rewritten as f power k minus summation L running from 0 to k minus 1 alpha L f L is equal to the 0 linear maps. Now, now this can be seen as x to the power k minus summation L running from 0 to k minus 1 alpha L x to the power L with composition of with the function f as the algebraic structure just we have seen, multiplying a polynomial and a linear map, and we are seeing that this polynomial and with the given linear map is going to be becoming a zero linear map. Okay. So that's what is the definition of the minimal polynomial is. So given a linear map f, we have shown that there exists a polynomial. In fact, we have shown that there exists a non-zero polynomial, say x power k minus summation L running from 0 to k minus 1 alpha L x to the power L. So you call it as m of x, non-zero polynomial m of x, such that m of f is equal to 0. So that is what we have proved. Yeah, non-zero polynomial such that m of f is equal to 0. One more thing that we have to observe here is, so the polynomial, the degree of this m of f, is k. Okay. And if you take any polynomial of degree less than k, then this property is not true. That we have to observe, because suppose there exists a polynomial of degree less than or equal to k minus 1, such that let's say suppose there exists a polynomial degree, okay. Of course, polynomial coming from f of x of degree less than or equal to k minus 1. Suppose say let's say a of x, such that a of f is 0. Suppose that tells you that, what does that mean? That will give rise to a linear combination of elements of I, f, f square etc. up to f to the power k minus 1, okay, contradicting the fact that this is linearly independent, because any linear combination of this giving rise to 0 map has to be the unique representation as 0 times of that, because this set is linearly independent, and the subset of this is also linearly independent. Therefore, this is not possible. Therefore, any polynomial, that's what we are proving. Therefore, we have shown that there exists a polynomial of degree. Suppose there exists a polynomial degree less than or equal to k minus 1, say a of x such that f of 0, then this contradicts the fact that I f etc. up to f to the power k minus 1 is linearly independent, and therefore we can as well say that it is a not only a non-zero polynomial such as m of 0, non-zero polynomial and least degree polynomial such that m of f is 0. Okay, that is of least degree. That is, any polynomial of degree less than that is not satisfying this property. Therefore, we can say that is a non-zero least degree polynomial such that m of f is 0. Now, when it comes to the uniqueness of this polynomial, we have a small thing. So before that, we just see a small result, so that will help us to prove the uniqueness of this minimal polynomial. Suppose there exists a polynomial m dash of x, say belonging to f of x, such that m dash of f is also 0. Okay. Suppose, okay. Then the claim is m of x divides m dash of x. Okay. That's what we claim. Suppose if this exists. Okay. So let's prove that. Now it's very clear that the degree of m dash of x cannot be less than or equal to k minus 1, because if suppose degree of m dash of x k less than or equal to k minus 1, and since m dash of f is 0, that contradicts that again I f etc. up to f to the power k minus 1 is really independent. Therefore, that cannot be possible. Therefore, the degree of m dash of x has to be at least k. Okay, at least k greater than or equal to k. Now we know that in f of x we have division algorithm. So we apply division algorithm between m of x and m dash of x. So we say that there exist unique q of x and r of x, okay, belonging to f of x, such that m dash of x can be written as q of x times of m of x plus r of x, where r of x is either a 0 polynomial or degree of r of x is less than the degree of m of x. We know degree of m of x is k, therefore degree of r of x is less than k. So these are two cases. Now suppose consider the case, second case. Suppose so we have to show that the claim is we have to show that m of x divides m dash of x, therefore indirectly we have to show that r of x is 0. Therefore this we have to show, therefore we have to prove, we will prove that this case is not possible by contradiction. So suppose degree of r of x is less than k, suppose. Now from this equation, say star, we can write r of x as m dash of x minus q of x into m of x. Now what is r of f by the algebraic structure that we have seen some time back? Then it's m dash of f minus q of f into m of f. Now this is 0, this is a 0 map, therefore all of it will become a 0 linear map, and therefore what we have just shown is r of f is 0 map. Now since r of f is 0, therefore degree of r of x cannot be less than k, because again that will contradict that I f etc of f square is f to the power k minus 1 is really independent. Therefore this case is a contradiction, that contradiction to the say that degree of r of x is less than k. Therefore degree is not less than k, and if degree of r of x is not less than k, therefore degree of r of x is 0, and hence m dash of x is equal to q of x into m of x, which says that m of x divides m dash of x. Therefore what we have just shown is, we have just shown the claim that m of x divides m dash of x. Therefore what it says is, if you have some other polynomial which divides, which satisfies this property of m dash of x is 0, then m of x has to be dividing the m dash of x, and therefore okay. So for the uniqueness of minimal polynomial, I mean we always used to prove by contradiction. Suppose there exists, let's say there are two polynomials, say m of x and m dash of x belonging to f of x, such that m of f is equal to m dash of f is equal to 0. Okay. Therefore by the result that we have just seen, that implies that m of x has to divide m dash of x, and m dash of x also has to divide m of x. And therefore what does this mean? This tells you that they can differ at most by a constant factor, because in polynomial in polynomial things, the constant polynomials, if you take a pair of constant polynomials, they divide each other. Okay. And therefore that's the only possibility you can think of by this condition. Therefore the two, if you take two polynomials such case, they can the maximum they can differ by a constant factor. In other words, I mean m of x is going to be some alpha times of m dash of x for some alpha in f. Okay. Or if you want to say m dash of x, you can also say that m dash of x is equal to alpha times of f. Okay. And therefore this can also be taken care, and by saying that this the coefficient, by saying that minimal polynomial, I mean by characterizing the minimal polynomial as a monic polynomial. Okay. So monic polynomial means that the coefficient of the highest degree has to be 1. I mean that is how we have seen in our case also. So we got we got x, this is nothing but this is what we got, the we got this monic polynomial, such that when you multiply with f, it becomes a 0 map. So the degree the highest degree is k is the highest degree, and the coefficient of the highest degree is 1. Okay. So that's what we say. I mean therefore by definition, the definition is, in order to get the uniqueness, even to take care up to the constant factor, the uniqueness is enforced by assuming that the minimal polynomial has to be a monic polynomial. Okay. And this is what we wanted to cover today. Thank you. So we have just covered the existence and uniqueness of a minimal polynomial for a given linear map f. Thank you.